back? I don't know what's going on. I gotta fix OBS apparently. I'll redo the stream key tomorrow, before tomorrow's stream.
The same size.
It's so fucking
Maybe you
annoying.
remember the TRAPPIST-1 system with a string of 7 roughly Earth mass
Is what it is.
Orbiting
Technology. At least I know what that fucking sound is now. That was the stream crashing.
Chains of super Earths or mini Neptunes. The thing we don't tend to find are a chain of terrestrial planets in an inner solar system followed by a chain of gas giants in the outer. The term peas in a pod describes this new picture in which planetary systems tend to have similar mass planets. If that's how such systems tend to form, usually, then it raises big questions about why our solar system didn't form that way. There are solid hypotheses for this, the most prominent being the Grand Tack hypothesis, which suggests that Jupiter migrated into the inner solar system in its early times, disrupting the larger worlds that were still developing there before retreating to the outer solar system again. The inner solar system then had to pull itself together from the depleted remnants of Jupiter's rampage. If this event resulted from some unusual gravitational interaction, say with a passing star, then it might mean that our planetary configuration is pretty rare. But we just don't know how rare. The main reason for that is a bit surprising. Jupiter-like worlds in Jupiter-like orbits are actually hard to confirm from past surveys, despite those planets being so much more massive than any terrestrial planet. The main challenge is the length of the year of such an outer system body, 12 years in the case of Jupiter. Now, the Doppler method can identify Jupiter-like companions from the wobble it induces in its star. It even measures the properties of that orbit with not even having to observe a full orbit. However, the Doppler method is just not well suited to the initial discovery of exoplanets. It can't track many thousands of stars at once in order to identify candidates. Now, the transit method can do that, for example, Kepler. But that method takes a lot longer to identify an exoplanet. Each transit is seen as just a little dip in the star's light, and we need to clock at least 3 of those dips to even recognize a candidate exoplanet from the regular spacing of the dips. The Kepler mission has no more than 4 years of observation on any given star, so it could potentially have flagged an exo-Mars, but definitely not an exo-Jupiter. Now, we could keep doing planetary transit observations until we have enough of a temporal basis and enough stars to see long-period gas giants. And the TESS satellite has picked up where Kepler has left off. But it'll still take decades to confirm an exo-Jupiter. Fortunately, we can do this a lot quicker by switching to yet another completely different method. As I mentioned, close planets cause their stars to wobble fast, good for the Doppler method. But more distant planets cause their stars to wobble far, and this raises an intriguing possibility. If we could actually see the stars moving, not just by their Doppler shifts, but by the actual changes in position, then we might be able to catch these large orbit exoplanets. To do this, we would need incredibly precise measurements of a star's position. And that's why we call this approach the astrometry method, where astrometry is just the science of precision measurement of celestial positions. So let's see how this could work. As I said, both star and planet orbit their mutual center of mass, their barycenter. The location of that barycenter depends only on the masses of both objects and their separation. It's always closest to the star, but the distance of the barycenter from the center of the star is proportional to 2 things: the relative mass of the planet and the distance of the star to the planet. Planets with larger orbits actually pull the barycenter further from the star than those with smaller orbits. And that's perfect because it makes the astrometry method more sensitive to large orbits, where both the Doppler method and the transit methods are better for small orbits. And that's what we want for finding exo-Jupiters. We do still have the problem that these sort of
If the
wide
stream
orbit
crashes again,
exoplanets
though, I'm just
also
fucking
have
calling
long
it.
orbital periods.
I'm not dealing with that
With
shit
the
again.
astrometry
So just let you
method,
know if the
we
stream fucking
actually see
crashes,
the orbit
I'm out.
playing out. So
We'll
we don't
be
have
back
to wait
fucking
for even
tomorrow.
a full
We'll fix
exo
it.
year to start to characterize the orbital parameters. Finally, astrometry can detect planetary systems with any alignment relative to us, whereas the transit method only catches those that happen to be conveniently oriented to produce said transits. And even the Doppler method is insensitive to systems that are flat against the plane of the sky. Okay, so we now have a third method for finding exoplanets that seems to shore up some of the weaknesses of the other two. So what have we done with this? Well, this is exactly how astronomers first confirmed that Sirius, the brightest star in the sky, has a faint white dwarf companion, Sirius B, and that was way back in 1844. Plenty of other binary stellar companions have been found that way, including things like companion black holes and neutron stars, but detecting an actual exoplanet this way is much harder due to the tininess of the star's wobble and the extreme resolution required to see that wobble. It wasn't until 2010 that we detected our first exoplanet via astrometry, but at that point Kepler was in full swing and just way more productive. What we needed was a dedicated astrometry satellite. Enter Gaia. Gaia was launched in 2013 and took data until March this year, over which time it scanned the entire sky over and over to make a census of 1 billion stars in the Milky Way. The main superpower of Gaia is precision astrometry. It does this in a cool way. Gaia has 2 telescopes actually on a spinning platform and achieves precise position measurements by converting the problem into a precise measurement of time, the time that a star crosses through the fields of view of both telescopes. Now, by combining 50 to 75 observations, Gaia can achieve a position resolution roughly the angular size of a US quarter on the moon. So
Damn.
Gaia's primary goal
pretty good.
was to measure stellar parallax. That's the apparent shift in a star's position as Earth orbits the Sun. And Gaia has enabled astronomers to calculate distances to actually 1.3 billion stars across the Milky Way. And combining this with velocities also measured for many of those stars, Gaia has given us this incredible dynamical map of a good chunk of our galaxy. But if Gaia can see a star's apparent wobble due to parallax, it should also be able to see an actual wobble due to the pull of the star's own planets. The first Gaia exoplanets found using astrometry are Gaia 4b and 5b, both super Jupiters with 12 and 21 times the mass of Jupiter respectively, both orbiting nearby low-mass stars. It was a painstaking task to sift these out of Gaia's third data release in 2023. First, astronomers had to identify wobbles consistent with exoplanets, and then rule out other causes, and then follow up the candidates with radial velocity measurements to confirm. But Gaia 4b and Gaia 5b are definitely there. These objects are unusual because they are super Jupiters orbiting stars that are smaller and less massive than the Sun. This combination of giant planet and small star was thought to be extremely rare, so we've already learned something new here.
Nice.
But then again, the wide orbits of these guys make them hard to see by other methods, so we never really knew much about such systems in the first place. What we do know is that Gaia can spot gas giants far from their stars. Gaia 4b and 5b have proved that. And in astronomy, where there's one, there are many. These planets mean that there's a whole population of undiscovered planets hiding in the Gaia data, waiting to be discovered. And that's going to happen following Gaia's data release 4 in December 2026. The Gaia DR4
So a year from now.
will be different because it'll include, for the first time, Gaia's time series measurements of stars' positions on the sky, rather than just the parallaxes.
Oh.
DR4 will also span 5.5 years, about twice as long as DR3. This enables the detection of planets more distant from their stars, because these take years to complete an orbit. Candidate exoplanets will be followed up with radial velocity Doppler observations, and these will confirm cases of interest and better measure the properties of the planets. But without Gaia, we wouldn't even know where to start looking in the first place. Okay, so how many exoplanets do we expect Gaia to find? Well, we talked to the astrophysicists who figured that out, Caleb Lanners and Josh Wynn, who recently published a study on exactly this subject. Based on simulated Gaia data, they predict that data release 4 will lead to 7,500 exoplanet detections, give or take a couple of thousand. This is likely to more than double the number of known exoplanets, which currently stands at about 6,000 confirmed, around half of which are from Kepler. Gaia DR4 will include only half of the data that the Gaia Space Telescope has collected. The full data set, DR5, will include astrometric measurements spanning 10.5 years and will be released in the early 2030s. The number of exoplanets will then explode even over the DR4 figure. There are two main reasons for this. The longer time span of observations makes Gaia sensitive to planets with longer orbital periods, so just more planets. Also, these longer orbital periods correspond to larger, physically larger orbits, and that means larger stellar wobbles. And the larger the wobble, the further away it can be detected by Gaia, making the mission sensitive over, well, a larger volume of space. Lamars and Wynn predict that DR5 will include a staggering 120,000 exoplanet
That's
detections.
crazy.
That's a 20-fold increase on the current
that's
exoplanet
insane.
numbers. But will we detect our solar system or one like it?
That's the question.
Gaia
That's
will
the
be
burning
sensitive to
question.
Jupiter-like worlds and those larger, so-called superjupiters, with orbits within 1 to 5 times the Earth-Sun distance, or astronomical units. Jupiter itself is 5 AU, and so Gaia should be able to spot a Jupiter analog. It won't be sensitive enough to detect the wobble due to Earth-like planets, but that's fine, because TESS will observe a chunk of Gaia's systems to get the inner systems of those. This combination of astrometric detections from Gaia and transit discoveries from Kepler and TESS will give us something close to a comprehensive census of possible planetary systems. That's going to allow us to really refine our understanding of the formation and evolution of these systems. In the case of the gas giants, for example, the ones that Gaia will discover, we may learn whether they form more like terrestrial planets from small bits clumping together, or more like stars with a large cloud of gas collapsing. But it's the combined knowledge from Gaia plus TESS that will teach us the most about our own solar system. It may be that we even find a true solar system analog out there, with an exo-Earth discovered by transit and an exo-Jupiter in the same system found through the wobble it produces. And if we don't find such a system, or find very few, that will confirm what some already suspect. The rarity of our solar system is really quite a rare beast, capable of nurturing a uniquely habitable world amid the rich planetary diversity that fills our galactic space-time.
Hell yeah.
We'd like to thank Henson Shaving for supporting
Henson Shaving is amazing. That's what I use. Anyways, that's another PBS Space-Time video, so go check them out. Give them a like, give them a view, give them a comment, all the good stuff. And then we'll move on to the final video of the day. Today's been a little bumpy with this fucking stream key passing out on me, motherfucker. Even though Kick and, like, Twitter and Rumble all seem to be fine, it's just Twitch is giving me some fucking
things are
dick
not
moves.
Normal. By that, I mean if you
Really?
go out in the world and start measuring
things aren't normal?
like human height,
Shit.
IQ, or the size of apples on a tree, you will find that for each of these things, most of the data clusters around some average value.
Yeah.
This is so common that we call it the normal distribution. But some things in life are not like this.
Nature shows power laws all over the place. That seems weird. Like, is nature tuning itself to criticality?
If you make a crude measure of how big is a world war by how many people it kills, you find that it follows a power law. The outcome will vary in size over 10 million, 100 million.
It's much more likelihood of really big events than you would expect from a normal distribution. And they will totally skew the average.
The system you're looking at doesn't have any inherent physical scale. It's really hard to know what's going to happen next.
The more you measure, the bigger the average is, which is really weird. It sounds impossible.
It's very important to try to understand, which game you're playing and what are the payoffs going to be in the long run.
In the late 1800s, Italian engineer Vilfredo Pareto stumbled upon something no one had seen before. See, he suspected there might be a hidden pattern in how much money people make. So he gathered income tax records from Italy, England, France, and other European countries, and for each country, he plotted the distribution of income. Each country he looked at, he saw the same pattern, a pattern which still holds in most countries to this day. And it's not a normal distribution.
If you think about a normal distribution like height, there's a clearly defined average, and extreme outliers basically never happen. I mean, you're never going to find someone who is, say, 5 times the average height. That would be physically impossible. But Pareto's income distributions were different. Take this curve for England. It shows the number of people who earn more than a certain income. The curve starts off declining steeply, most people earn relatively little, but then it falls away gradually, much more slowly than a normal distribution would, and it spans several orders of magnitude. There were people who earned 5 times, 10 times, even 100 times more than others. That kind of spread just wouldn't happen if income were normally distributed. Now, to shrink this huge spread of data, Pareto calculated the logarithms of all the values and plotted those instead. In other words, he used a log-log plot. And when he did that, the broad curve transformed into a straight line. The gradient was around negative 1.5. That means each time you double the income, say from 200 pounds to 400 pounds, the number of people earning at least that amount drops off by a factor of 2 to the power of 1.5, which is around 2.8. And this pattern holds for every doubling of income.
Damn,
so
that's
Pareto could
fucked.
describe the distribution of incomes with one simple
Doesn't that
equation.
mean it's
The number of
fabricated?
people who earn an income greater than or equal to X is
That's
proportional
a
to
not
1 over
not
X to the
nat
power
like
of 1.5.
Now,
Like,
that's
absolutely
what Pareto saw for
fabricated?
England, but he performed the same analysis on data from Italy, France, Prussia, and a bunch of other countries.
World
And he
government,
saw
world
the same
government,
thing
world
again
government.
and again. Each time, the data transformed into a straight line, and the gradients were remarkably similar. That meant Pareto could describe the income distribution in each country with the same equation, 1 over the income to some power, where that power is just the absolute gradient of the logarithmic graph. This type of relationship is called a power law. When you move from the world of normal distributions to the world of power laws, things change dramatically. So to illustrate this, let's take a trip to the casino to play 3 different games. At table number 1, you
Gambling!
get 100 tosses of a coin. Each time you flip and it lands on heads, you win $1. So the question is, how much would you be prepared to pay to play this game?
Well, we need to work out how much you'd expect to win in this game and then pay less than that expected value. So the probability of throwing a head is 1/2. Multiply that by $1 and multiply that by 100 tosses. That gives you an expected payout of $50. So you should be willing to pay anything less than $50 to play this game. Sure, you might not win every time, but if you play the game hundreds of times, the small variations either side of the average will cancel out, and you can expect to turn a profit. One of the first people to study this kind of problem was Abraham de Moivre in the early 1700s. He showed that if you plot the probability of each outcome, you get a bell-shaped curve, which was later coined the normal distribution.
Normal distributions, the traditional explanation is that when there are a lot of effects that are random, that are adding up, that's when you expect normals. So like how tall I am depends on a lot of random things about my nutrition, about my parents' genetics, all kinds of things. But if these random effects are additive, that is what tends to lead to normals.
At table number 2, there's a slightly different game. You still get 100 tosses of the coin, but this time, instead of potentially winning $1 on each flip, your winnings are multiplied by some factor. So you start out with $1, and then every time you toss a head, you multiply your winnings by 1.1. If instead the coin lands on tails, you multiply your winnings by 0.9. And after 100 tosses, you take home the total. That is the dollar you started with times the string of 1.1s and 0.9s. So how much should you pay to play this game?
Well, on each flip, your payout can either grow or shrink, and each is equally likely each time you toss the coin, so the expected factor each turn is just 1.1 plus 0.9 divided by 2, which is 1. So if you start out with $1, then your expected payout is just $1. That means you should be willing to pay anything less than $1 to play this game, right? Well, if you look at the distribution of payouts, you can see that you could win big. If you tossed 100 heads, you'd win 1.1 to the power of 100. That's almost $14,000. Although the chance of that happening is around 1 in 10 to the power of 30. You'd be more likely to win the lottery 3 times in a row. On the other hand, the median payout is around 61 cents. So if you're only playing the game one time and you want even odds of turning a profit, well then you should pay less than 61 cents. Though either way, if you played the game hundreds of times, your payout would average out to $1. Now watch what happens if we switch the x-axis from a linear scale to a logarithmic scale. Well then you see the curve transforms into a normal distribution. That's why this type of distribution is called a log normal distribution.
When random effects multiply, if I have a certain wealth, and then my wealth goes up by a certain percentage next year because of my investments, and then the year after that, it changes by another random factor. As opposed to adding, I'm multiplying year after year. If you have a big product of random numbers, when you take the log of a product, that's the sum of the logs. So what was a product of random numbers then gets translated into sums of logs of random numbers. And that's what leads to this so-called log normal distribution. And log normal distributions produce big inequalities. You don't just see a mean, you see a mean with a big long tail. It's much more likelihood of really big events, in this case, tremendous wealth being obtained, than you would expect from a normal distribution.
The reason this curve is so asymmetric is because the downside is capped at 0, so at most you could lose $1. But the upside can keep growing, up to nearly $14,000. Now let's go on to table 3. Again, you'll be tossing a coin. But this time, you start out with $1 and the payout doubles each time you toss the coin. And you keep tossing until you get a heads. Then the game ends. So if you get heads on your first toss, you get $2. If you get a tails first and then hit a heads on your second toss, you get $4. If you flipped 2 tails and then a head on your third toss, you'd get $8, and so on. If it took you to the nth toss to get a heads, you would get 2 to the n dollars. So how much should you pay to play this game? Well, as in our previous example, we need to work out the expected value. So suppose you throw a head on your first try. The payout is $2, and the probability of that outcome is a half. So the expected value of that toss is $1. If it takes you 2 tosses to get a heads, then the payout is $4, and the probability of that happening is 1/4. So again, the expected value is $1. We also need to add in the chance that you flip heads on your third try. In that case, the payout is $8, and the probability of that happening is 1/8. So again, the expected value is $1. And we have to keep repeating this calculation over all possible outcomes. We have to keep adding $1 for each of the different options for flipping the coin, say 10 times until it lands on heads, or 100 times before you get heads. I know it's extremely unlikely, but the payout is so huge that the expected value of that outcome is still $1. So it still increases the expected value of the whole game. This means that, theoretically, the total expected value of this game is infinite. This is known as the St. Petersburg paradox. If you look at the distribution of payouts, you can see it's uncapped. It spans across all orders of magnitude. You could get a payout of $1,000, $100,000, or even $1 million or more. And while $1 million payout is unlikely, it's not that unlikely, it's around 1 in a million. Now, if you transform both axes to a log scale, you see a straight line with a gradient of -1. The payout of the St. Petersburg paradox follows a power law. The specific power law in this case is that the probability of a payout x is equal to x to the power of -1, or 1/x. in the previous games, when you have a normal distribution or even a log normal distribution, you can measure the width of that distribution, its standard deviation. And in a normal distribution, 95% of the data fall within 2 standard deviations from the mean.
Yep.
But with a power law, like in the St. Petersburg paradox, there is no measurable width. The standard deviation is infinite.
This makes power laws a fundamentally different beast with some very weird properties.
Imagine you take a bunch of random samples and then average them, and then take more random samples and average them. You'll find that the average keeps going up. It doesn't converge. And the more you measure, the bigger the average is, which is really weird. It sounds impossible, but it's because it has such a heavy tail, meaning the probability of really whopping big events is so significant that if you keep measuring, occasionally you're going to measure one of those extreme outliers, and they will totally skew the average. It's sort of like saying, you know, if you're standing in a room with Bill Gates or Elon Musk, the average wealth in that room
Goes up by
is
like,
going to be $100 billion
yeah.
or something, because the average is dominated by one outlier.
And that same idea, one outlier can dominate the average, shows up online too. A handful of companies, servers, and data centers hold the personal information of millions of people. So
Yup.
when one of them gets hacked, it can have ripple effects across the whole network.
Yo!
We've had scammers get a hold of email addresses and phone numbers of writers on our team and then send them messages pretending to be me. That is where today's sponsor, NordVPN, comes in. NordVPN encrypts your internet traffic so your personal data stays private, even when the wider system isn't. It protects you from hackers, trackers, and malware with threat
Always
protection, even
use
when
a
you're not connected
VPN.
to a VPN.
It's the
Within
way
just
of
15
the
minutes
world.
of registering a new email, we saw that 5 leaks had already been detected. NordVPN lets you browse securely from anywhere in the world by routing your connection through encrypted servers in over 60 countries. You can try it completely risk-free with a 30-day money-back guarantee. Just scan this QR code or go to nordvpn.com/veritasium to get a huge discount on a 2-year plan plus 4 extra months free. That's nordvpn.com/veritasium for a huge discount. I'll put the link down in the description. I'd like to thank NordVPN for sponsoring this video, and now back to power laws. So why do you get a power law from the simple St. Petersburg setup?
If you look at the payout x, you can see it grows exponentially with each toss of the coin, x equals 2 to the n. But if you look at the probability of tossing the coin that many times to get
It
a
goes
heads,
the
you can see
opposite.
that this probability shrinks exponentially. So the probability of flipping a coin n times is a half to the power of n. But we're not really interested in the number of tosses, we're interested in the payout. Now we know that x equals 2 to the n, so instead of writing 2 to the n in our probability equation, we can just write x. So we end up with this. The probability of a payout of x dollars is equal to 1 over x, or in other words, x to the power of -1.
You put them together, the exponentials conspire to make a power law. And that's a very common thing in nature, that a lot of times when we see power laws, there are 2 underlying exponentials that are dancing together to make a power law.
One example of this is earthquakes. If you look at data on earthquakes, you find that small earthquakes are very common.
Yeah, but then you get that like
earthquakes of increasing magnitudes
9.0
become
that's like
exponentially
1,000 times
But the
more
destruction
because
that
of the
earthquakes cause
magnitude
is
of the
not
Richter
proportional
scale.
to their magnitude. It's proportional to the energy they release. And as earthquakes grow in magnitude, that energy grows exponentially.
So there's this exponential decay in frequency of earthquakes of a given magnitude, and an exponential increase in the amount of energy released by earthquakes of a certain magnitude. So when you combine those 2 exponentials to eliminate the magnitude, what you find is a power law.
But power laws also reveal something deeper about the underlying structure of a system. To see this in action, let's go back to the third coin game and the St. Petersburg paradox.
Now you can draw all the different outcomes as a tree diagram, where the length of each branch is equal to its probability. So starting with a single line of length 1, and then a half for the first 2 branches, a quarter for the next 4, and so on. Now, when you zoom in, you keep seeing the same structure repeating at smaller and smaller scales. It's self-similar, like a fractal. And that's no coincidence. We see the same fractal-like pattern in the veins on a leaf, river networks, the blood vessels in our lungs, even lightning. And in all of these cases, we can describe the pattern with a power law.
That's
Power laws and
fucking insane.
fractals are intrinsically
The
linked.
world is so...
That's
I
because
love how
power laws
crazy
reveal
the world
something
actually
fundamental
is.
about a system's structure.
So crazy.
So I've got a magnet and I've got a screw. And you'll notice if I bring them close together, then the screw gets attracted to the magnet. And that's because there's a lot of iron in it, which is ferromagnetic. But watch what happens if I start heating this up. Trying to... Oh. You see that? Ah, there it went. There it went. You see, you heat it up and suddenly it becomes non-magnetic. To find out what happened, let's zoom in on this magnet.
Inside a magnet, each atom has its own magnetic moment, which means you can think of it like its own little magnet or compass. If one atom's moment points up, its neighbors tend to point that way too, since this lowers the system's overall potential energy. Therefore, at low temperatures, you get large regions called domains where all the moments align. And when many of these domains also align, their individual magnetic fields reinforce to create an overall field around the magnet. But if you heat up the magnet, each atom starts vibrating vigorously. The moments flip up and down, and so the alignment can break down. And when all the moments cancel out, then there's no longer a net magnetic field.
Now, if you have the right equipment, you can balance any magnetic material right on that transition point, right between magnetic and non-magnetic. This is called the critical point, and it occurs at a specific temperature called the Curie temperature. I asked Casper and the team to build a simulation to show what's going on inside the magnet at this critical point.
Each pixel represents the magnetic moment of an individual atom. Let's say red is up and blue is down. Now, when the temperature is low, we get these big domains where the magnetic moments are all aligned, and you get an overall magnetic field. But if we really crank up the temperature, then all of these moments start flipping up and down, and so they cancel out, and the magnet loses its magnetism. So that's exactly what happened in our demo. But if we tune the temperature just right to that Curie temperature, then the pattern becomes way more interesting.
This looks like a map.
Like a map?
Yeah, it almost looks like the Mediterranean or something. It's almost stable. Like, atoms that are pointing one way tend to point that way for a while, but there's clearly fluctuations as well, so domains are constantly coming and going. It's both got some elements of stability and some persistence over time, some features which are consistent, but it's also not locked in place,
Right.
because you notice changes over time.
If you zoom in, you find that the same kinds of patterns repeat at all scales. You've got domains of tens of atoms, hundreds, thousands, even millions. There's just no inherent skill to the system. That is, it's skill-free. It's just like a fractal. And if you plot the size distribution of the domains, you get a power law.
The underlying geometry suddenly shows a fractal character that it doesn't have on either side of the phase transition. Right at the phase transition, you get fractal behavior, and that pops out as a power law.
In fact, whenever you find a power law, that indicates you're dealing with a system that has no intrinsic scale. And that is a signature of a system in a critical state, which it turns out has huge consequences.
See, normally in a magnet, below the Curie temperature, each atom influences only its neighbors. If one atom's magnetic moment flips up, then that means that its neighbors are slightly more likely to point up too. But that influence is local. It dies out just a few atoms away. But as the magnet approaches its critical temperature, those local influences start to chain together. One spin nudges its neighbor, and that neighbor nudges the next, and so on, like a rumor spreading through a crowd. And the result is that the effective range of influence keeps expanding, and right at the critical point, it becomes effectively infinite. A flip on one side can cascade throughout the entire material. So you get these small causes, just a single flip, to reverberate throughout the entire system.
And it gets right into that point where the system is maximally unstable. Anything can happen. It's also maximally interesting in a way. It means the system is most unpredictable, most uncertain. It's really hard to know what's going to happen next. And that seems to be a natural procedure that happens in many different systems in the world.
One such system is forest fires. In June 1988, a lightning strike started a small fire near Yellowstone National Park. This was nothing out of the ordinary. Each year, Yellowstone experiences thousands of lightning strikes. Most don't cause fires, and those that do tend to burn a few trees, maybe even a few acres, before they fizzle out. 3/4 of fires burn less than 1/4 of an acre. The largest fire in the park's recent history occurred in 1931. That burned through 18,000 acres, an area slightly larger than Manhattan. But the 1988 fire was different. That initial spark spread, slowly at first, covering several thousand acres. Then, over the next couple of months, it merged with other small fires to create an enormous complex of megafires that blazed across 1.4 million acres of land. That's around the size of the entire state of Delaware.
Damn.
That's 70 times bigger than the previous record, and 50 times the area of all the fires over the previous 15 years combined.
Shit.
So what was so special about the 1988 fires? Well, to find out, we made a forest fire simulator.
We've got a grid of squares, and on each square, either a tree could be there, it could grow, or it could not be there. There's going to be some probability for lightning strikes. So, the higher the probability, the more fires we're going to have. We can run this.
So trees are growing.
Trees are growing.
Forest is filling in. Nice. Getting pretty dense.
What do you expect is going to happen?
I expect to see some fires. Probably, now that... Oh, that was good. That was a good little fire. Whoa. Whoa. No way. Whoa, that's crazy. You haven't adjusted the parameters, right? It's just like...
Not yet. Not yet.
This seems like a very critical situation just by itself. I say that because of how big that fire was.
This sort of system will tune itself to criticality, and you can see it start to happen. So right now, I think is a good moment where you have basically domains of a lot of different sizes. And then one way to think about it is if some of these domains become too big, then you get a single fire, like that one, perfectly timed.
Burns them
It's
all
just
out.
going to propagate throughout the whole thing and burn it back
And
down.
that's
a little.
the
But then
potency
if
of
it goes
density,
too
and that's the
hard,
reason
then
why
now
you
you've
want to
got all
have
these domains where there are
different
no trees,
types
and
of
so it's gonna,
trees and different
grow
spread and
again
stuff
to
like
bring it
that.
back to that
And it's like one of the main
critical
problems
I
for
can
main
see
forest
how
fires
it's the
in
feedback
like
mechanism,
rural and urban
right? The
areas
fire
is
gets
like
rid
the
of
way
all the
we
trees, and then
planted
there's nothing left
trees
to
over
burn,
periods of time.
And then that has to fill
And
in
like
again.
the
Yeah.
Yeah,
planting
but
the
if
same
there
types
hasn't
of
been a
trees without
fire,
having
then the forest
diversity.
gets too thick, and then it's ripe for this sort of
Massive fire.
fire.
For
just
a magnet,
spreads
you have to
through everything.
painstakingly tune it to the critical point, but the forest naturally drives itself there. This phenomenon is called self-organized criticality. Yeah, and if you let it run, what you get is, again, a power law distribution. So this is log-log. So it should be a straight line.
That kind of stuff seems so totally random and unpredictable, and it is in one way, and yet it follows a pattern. There's a consistent mathematical pattern to all these kind of disasters. It's shocking.
Is there something fractal about this?
Mostly in terms of the, I guess, domains of the trees when you're at that critical state. So you get very dense areas, you get non-dense areas. And as a result, when a single lightning bolt strikes, you can get fires of all sizes. Most often, you get small fires of 10 or fewer trees burning. A little less frequently, you get fires of less than 100 trees. And then, every once in a while, you get these massive fires that reverberate throughout the entire system.
Now, you might expect that because the fire is so large, there has to be a significant event causing it. But that's not the case, because the cause for each fire is the exact same.
Yeah.
It's a single lightning strike.
It's just whether the
only
clustering
difference
allows
is where it
it.
strikes and the exact makeup of the forest at that
Yeah.
time. So, in some very real way, the large fires are nothing more than magnified versions of the small ones. And even worse, they're inevitable. So, what we've learned is that for systems in a critical state, there are no special events causing the massive fires. There was nothing special about the Yellowstone fire.
In 1935, the U.S. Forest Service established the so-called 10 a.m. policy. The plan was to suppress every single fire by 10 a.m. on the day following its initial report. Now, naively, this strategy makes sense. I mean, if you keep all fires under strict control, then none can ever get out of hand. But it turns out this strategy is extremely risky.
So let's say we're going to bring down the lightning probability. So it's very small, only 1 in a million right now. And we're also going to crank up
the tree growth a little bit. Now, what do you think is going to happen?
We're gonna get some big fires, I would imagine. Like a lot of not fire and then some huge fires. Yeah.
Yep.
Oh boy.
So nowadays, the fire service has a very different approach. They acknowledge that some fires are essential to make the mega fires less likely. So they let most small fires burn and only intervene when necessary. In some cases, they even intentionally create small fires to burn through some of the buildup.
Yep.
Though it could take years to return the forest to its natural state after a century of fire suppression.
But it's more than just the Earth's forests that are balanced in this critical state.
Every day, the
Rock
Earth's crust is
slides?
moving and rearranging
Oh,
itself.
just earthquakes,
Stresses
maybe.
build up slowly as tectonic plates rub against each other. Most of the time, you get a few rocks crumbling. The ground might move just a fraction of a millimeter. But the stresses dissipate in mini earthquakes that you wouldn't even feel.
There are really tiny earthquakes that are happening right now beneath your feet. You just can't feel them because they're very small. But they are earthquakes. They're driven by small slipping movements in the Earth's crust.
But sometimes, those random movements can trigger a powerful chain reaction.
In Kobe, Japan, the morning of January 17th, 1995 seemed just like any other.
This is the
This was a
8.1.
peaceful city, and although Japan as a country is no stranger to earthquakes, Kobe hadn't suffered a major quake for centuries. Generations grew up believing the ground beneath them was stable. But that morning, deep underground, a stress released nearby the Nojima fault line. The stress propagated to the next section of the fault, and the next. Within seconds, the rupture cascaded along 40 kilometers of crust, shifting the ground by up to 2 meters and releasing the energy equivalent of numerous atomic bombs. The resulting quake destroyed thousands of homes, along with most major roads and railways leading into the city. It killed over 6,000 people and forced 300,000 from their homes.
How far it goes depends a lot on chance and the organization of all that stress field in the Earth's crust. And it just seems to be organized in such a way that it is possible oftentimes for the earthquake to trickle along an avalanche along a long way and produce a very large, unusual earthquake. But if you look at the process behind that earthquake, it is exactly the same physical process. It's just that the earthquake generating process
That's so
naturally
crazy.
produces events that range over an enormous range of scale. And we're not really used to thinking about that.
We have this ingrained assumption that we can use the past to predict the future. But when it comes to earthquakes or any system that's in a critical state, that assumption can be catastrophic because they're famously unpredictable. So how can you even begin to model something like the behavior of earthquakes?
In 1987, Danish physicist Per Bak and his colleagues considered a simple thought experiment. Take a grain of sand and drop it on a grid. Then keep dropping grains on top, until at some point the sand pile gets so steep that the grains tumble down onto different squares.
What they looked at was the size of these, what they were calling avalanches, these reorganizations of numbers of grains of sand. They asked for, how often do you see avalanches of a certain size?
This is the most simple version of a sand pile simulator that you could almost imagine. We're gonna drop a little grain of sand, at first always in the center, and then it's just gonna keep going up. For 1 grain, it'll be fine. For 2 grains, it'll be fine. 3 grains, it'll be fine, but it's on the edge of toppling. And then when it reaches 4 or more, it's gonna basically go. Feels a bit like a, I don't know, pulsing thing. Like something's trying to escape or something. Very video game-like. That seemed pretty crazy. And it is symmetrical.
Yeah, nice geometric features.
So this might be interesting because right now we paused it at a point where this middle one is gonna go. And then you look around it and you see, essentially you can think of these brown or these 3 tall grain stacks as being maximally unstable. They're about to go. And so you could think of them as these fingers of instability. If anything touches them, the whole system, like they're just gonna go.
I see it propagating out.
It's cool seeing it slower. I feel like you can see several waves propagating at the same time.
Some people have reasoned that the Earth's crust becomes riddled with similar fingers of instability, where you get stresses building up. And then when one rock crumbles, it can propagate along these fingers, potentially triggering massive earthquakes. If you look at the data, there's some even more compelling evidence that links the sand pile simulation to earthquakes.
Let's say instead of dropping it at the center, pretty unrealistic to have it drop at the center, I'm gonna drop at random.
Yeah. That is crazy.
You can actually see it tune itself to the critical state. Like at the start, you only see these super tiny avalanches.
Yeah.
And then now it's everything.
It has to build up.
We can slow down a little. Oh, and that's a super clean power law.
There are events of all sizes. One grain of sand might knock over just a few others, or it could trigger an avalanche of millions of grains that cascade throughout the entire system. And if you look at the power law you get from the sand pile simulation, it closely resembles the power law of the energy released by real earthquakes. But if you look at the sand pile experiment more closely, it doesn't just resemble earthquakes.
What does it remind you of?
Forest fires.
Right? Feels like it's the exact same behavior.
That's the really surprising thing. And that's why this little paper with a sand pile was published in the world's top journal, because it did something that people just didn't really think was possible.
Now, what's ironic is if you look at real sand piles, they don't behave like this.
Okay, you said sand. I'm going to do an experiment on a real sand pile. And of course, it doesn't follow a power law distribution of avalanches at all. It's totally wrong. Per Bach naturally gets a chance to reply to the criticism. And he says, I'm pretty close to quoting, he says, self-organized criticality only applies to the systems it applies to. So he doesn't care. The fact that his theory is not relevant to real sand piles, so what? Get out of my face. He's interested in bigger fish to fry than sand piles. It's like you're taking me too literally. I'm talking about a universal mechanism for generating power laws, and the fact that it doesn't work in real sand is uninteresting to him. I thought that took some real nerve.
Yeah, that's not something you generally get out of someone
The Earth.
as a response to
And
criticism.
the Earth going around the
It
sun.
should
That's a
be
very
more, especially in the
complex system. You've
scientific
got all
world.
the-
But
you've got the
science
molten
is so full
core,
of fucking
everything's sloshing
dogma and
around, and you've got
bullshit.
Oceans, and you've even
That's why I
got
love
the
stuff
moon
like
going
this,
around the
because
Earth,
it's like,
which in theory,
it's
you
just
know,
presenting you the
all
raw
should
data
affect
and
the
then
exact motion
experimenting
of the
to see if it's correct or not.
But
So you're literally doing the
Newton
science
ignored
in
all
real
of that. All
time
he
with
looked
all
at
the evidence
was
in front of
just
you.
a single parameter, essentially, the mass of the Earth. And with that, he could correctly, for the most part, predict how the Earth was going to go around the sun. Similarly here, there are people that have looked at these phenomena that go to the critical state. In this case, it's self-organized criticality, because it brings itself there. And what they find is that there's this universal behavior where it doesn't even really matter what the subparts are. You just get the behavior that's the exact same.
At that critical point, when all the forces are poised and the system is right on that delicate balance between being organized, highly organized, or being totally disorganized, it turns out that almost none of the physical details about that system matter to how it behaves. There's just a universal behavior that is irrespective of what physical system you're talking about. The term that was used is called universality. And it's kind of a miracle. It means you can make extremely powerful theories without involving any technical details, any real details of the material.
What this means is that you could have these systems that on the surface seem totally different. But when you get to the critical point, they all behave in the exact same way.
The other thing you could do is instead of this being trees, you could imagine it being people. And the thing that's spreading
Is disease.
is disease. Yeah.
You almost get something for nothing at these critical points.
See, many of these systems fall into what's known as universality classes. Some of them you need to tune to get there, like magnets at their Curie temperature, or fluids like water or carbon dioxide at their critical point. But some other systems seem to organize themselves to criticality, like the forest fires, or sand piles, or earthquakes. But what's crazy is that if you succeed in understanding just one system from a class, then you know how all the systems in that class behave. And that includes even the crudest, simplest toy models, like the simulations we've looked at. So you can model incredibly complex systems with the most basic of models. And some people think this critical thinking applies even further.
When we look around the world, there are lots of systems
Could it
that show
apply
the
to
same
consciousness
power law
as
behavior
well?
that we see in these critical systems. It's in
Are you a
everything
person
from
who is on the
DNA
natural
sequencing
deviant,
to
or
the
are you on
distribution
this
of species
critical,
in an ecosystem
you know,
to the
process?
size
Is that a
of mass
creativity
extinctions throughout
thing
history.
for people who are
We
truly
even
creative?
see the same behavior
Like I
in
would
human
consider us
systems,
as a
like
community?
the populations of cities, fluctuations in stock prices, citations of scientific papers, and even the number of deaths in wars.
So some people argue that these systems, and perhaps many parts of our world, also organize themselves to this critical point.
So the fact that all these natural hazards, as they call them, floods, wildfires, and earthquakes, they all follow power law distributions, means that these extreme events are much more common than you would think based on normal distribution thinking.
If you find yourself in a situation or an environment that is sort of governed by a power law, how
That
should
would
you
be like
change your
Twitch.
behavior?
The only way to
If you
grow is to
have
snowball like that.
events with one of these parallel distributions, what you're seeing most of the time is small events, and this can lull you into a false sense of security. You think you understand how things are going. You know, floods, for example, there are a lot of small floods, and then every once in a while there's a huge one. One response to this is insurance. That insurance is designed precisely to protect you against the large, rare events that would otherwise be very bad. But then there's the other side of that picture, which is you're the insurance company that needs to insure people. And they have a particularly difficult job because they have to be able to say how much to charge so that they have enough money to pay out when the big bad thing comes along.
In 2018, a forest fire tore through Paradise, California. It became the deadliest and most destructive fire in the state's history. But the insurance company, Merced Property and Casualty, hadn't planned for something that huge.
Yep.
And when the claims came in, they just didn't have the reserves to pay out. So just like that, the company went bust.
But while extreme events can cripple some companies, there are entire industries that are built on power law distributions. Between 1985 and 2014, private equity firm Horsley Bridge invested in 7,000 different startups. And over half of their investments actually lost money. But the top 6% more than 10x'd in value and generated 60% of the firm's overall profit. In fact, the best venture capital firms often have more investments that lose money. They just have a few crazy outliers that show extraordinary growth, a few outliers that carry the entire performance.
That sounds like fucking
Y
YouTube
Combinator
too.
calculated that 75% of their returns came from just 2 out of the 280 startups they invested in. So venture capital is a world that depends
Just
on taking
one-
risks.
one
in the
video
hope
away
you'll
from
get a
that
few
fucking
of these
break.
extreme outliers which outperform all of the rest of the investments combined.
Book publishers operate in a similar fashion. Most titles flop, but in 1997, a small independent UK publisher called Bloomsbury took a chance on a story about a boy wizard.
Yup, Harry Potter.
The boy's name, of course, was Harry Potter, and now Bloomsbury is a globally recognized brand. We see a similar pattern play out on streaming platforms. On Netflix, the top 6% of shows account for over half of all viewing hours on the platform. On YouTube, less than 4% of videos ever reach 10,000 views.
Yep.
But those videos account for over 93% of all views.
All these domains follow the same principle that Pareto identified over 100 years ago, where the majority of the wealth goes to the richest few. The entire game is defined by the rare runaway hits.
But not every industry can play this game.
It's like a
If you're running
survivorship
restaurant,
bias
you need
on
to fill tables night after night.
billionaires and
you can't
millionaires,
have one particular
which I think
busy
people
summer evening
overlook
that brings
in
in millions
the
of customers to
aspect
make
of
up for a bunch
wealth.
of quiet nights. Over a year, the busy nights and quiet ones balance out, and you're left with the average. Airlines are similar. An airline needs to fill seats on each flight. You can't squeeze 1 million passengers onto one plane, so it's the average number of passengers over the year that defines an airline's success.
We're used to living in this world of normal distributions and you act a certain way.
Yeah.
But as soon as you switch to this realm that is governed by a power law, you need to start acting vastly different. It really pays to know what kind of world or what kind of game you're playing.
That is good. That's good, yes. You should come on camera and just say that, just like that. You were on camera, you just did do it.
If you're in a world where random additive variations cancel out over time, Then you get a normal distribution. And in this case, it's the average performance, so consistency, which is important. But if you're in a world that's governed by a power law where your returns can multiply and they can grow over many orders of magnitude,
and the growth is
then
basically
it might make
infinite,
sense to take some riskier
you could wind
bets
up
in the
with a
hope
video that has
one
a
of them pays
billion
off
views.
huge. In other words, it becomes more important to be persistent than consistent.
Though, as we saw in the second coin game, totally random multiplicative returns give you a log normal distribution, not a power law. To get a power law, there must be some other mechanism at play. In the early 2000s, Albert Laszlo Barabashi was studying the internet, and to his surprise, he found that there was no normal web page with some average number of links. Instead, the distribution followed a power law. A few sites like Yahoo had thousands of times more connections than most of the others. Barabashi wondered what could be causing this power law of the internet, so he made a simple prediction. As new sites were added to the internet, they were more likely to link to well-known pages. To test this prediction, he and his colleague Reka Albert
100% Twitch, 100%
they
fucking
started with a network of just a
YouTube
few
and shit.
nodes, and gradually they added new nodes to the network, with each new node more likely to connect to those with the most links. As the network grew, a power law emerged. The power was around -2, which almost exactly matched the real data of the internet.
Look at that.
That's fun.
It's still so satisfying. This will basically also distribute a power law. One of the ideas here is that, this could be individuals or even companies. And so if you're more likely to become more successful or more well-known, the more known or successful you already are, then you're going to get this sort of runaway effect where you get a few that sort of dominate, the distributions.
I wonder if part of the takeaway is, like, if you're playing some sort of game that is dominated by a power law, then you better do the work, as much of it as early as possible, so you get to benefit from the snowball effect, essentially.
Yeah, I guess that's a good idea. I'm not sure whether you can control it. Human beings like to think of ourselves as being a bit special.
Yeah.
And that maybe somehow, because we're intelligent and have free will, we will escape the provenance of the laws of physics and order and organization. But I think that's probably not the case. So if you look at the number of world wars, and if you make a crude measure of how big is a world war by how many people it kills, which is a bit macabre, but still, you find that, again, it follows a power law, virtually identical to the power law you find in stock market crashes.
So if the world is shaped by power laws, then it feels like we're poised in this kind of critical state, where two identical grains of sand, two identical actions can have wildly different effects. Most things barely move the needle, but a few rare events totally dwarf the rest.
Yeah.
And that, I
Hey,
think, is the
Citation
most
Chat. Hey,
important
boy,
lesson.
how's it going?
If you
How
choose
are
to
ya?
pursue areas
Welcome.
governed by the
Oh,
normal
welcome.
distribution,
Just watching
you
a
can pretty much
Veritasium video
guarantee average results.
about,
But if you select pursuits ruled by power laws, the
power
goal
laws
isn't
and
to
normal
avoid this,
distribution,
it's to make repeated
graphing out
intelligent bets.
systems and
Most of them will
how
fail,
things work.
But you only need one wild success to pay for
I'm
all
doing
the rest.
fantastic.
And the thing is that beforehand, you cannot know which bet it's going to be because the system is maximally unpredictable.
Yeah.
It could be that
We're
your next bet
literally
is
talking
nothing, it
Twitch
could
and
do a little
YouTube
bit,
here.
or it could
They run
change
along
your
the
entire
same
life.
kind of power
In
law
fact,
system.
around 3
Once
years
you
ago,
get
I was
something
reading
that
this little
takes
book,
off,
and in the
it
book,
elevates
there was this little line
everything
saying something
else
like,
and it becomes
"One
part of
idea
that
could
sphere,
transform
right?
your entire
But if you
life."
don't have anything to grasp
right
onto, you
underneath
have no
that, I
growth.
would send an email to Veritasium.
A couple days later, I wrote an email to Derek saying, "Hey, Derek, I'm Casper. I study physics and I can help you research videos." I didn't hear back for 4 weeks, so I was getting pretty sad and just wanted to forget about it and move on. But then a couple days later, I got an email back saying, "Hey, Casper, we can't do an internship right now, but how would you like to research, write, and produce a video as a freelancer?" So I did, and that's how I got started at Veritasium.
Hell yeah. Veritasium is growing so much. It's crazy. I love Veritasium. They're so good. I love science shows like this that really amp you up, right? Hell yeah. Alright, and now we can move on to the final video of the day, because we're not going to do art today. I'm too tired for that. Excuse me. We will do. See, small shifts solve 90% of my pacing problems. Hi, dude. Rahoo. Yo, what's up, bro? Welcome, welcome. We're gonna have an ad break in a bit here, so we're just gonna chill out. I'm from your mom. bitch. That's where I'm from. Oh. Long lost brother. I am from India. Oh, very good. Oh, hello. Hello, sir. Welcome, welcome. What are you doing? What are you up to? Are you a writer? Are you a reader? Are you a purveyor of stories? Do you enjoy creativity and imagination? Are you an explorer of the world of words? Hello, I am Intoxication and welcome. Here we do a little bit of beta reading. No, unfortunately, I cannot do Hindi. That is the one thing I am very short on. The only thing I can do is we could get this out going right now. I need to turn this into a thing and I cannot remember which one it is because I am so bad at this, but I believe it is an E. Node. It's ER? Or is it UR? Oh, the fuck, I don't know. Or I'd probably never be able to find it. Ah, it was ear. Ear, this is the one. This is the one. This is some fucking banger shit. Yeah, man, we like to have a good time here, that's for sure. Like, I really wish I could sing. And I wish I knew Hindi. It would be so fucking awesome. But I have way too much other shit that I have to do. I just can't spend time on that. This was all Bomb Dropper. He's the one who recommended this, because I was like, what is that one song? And he's like, well, there's more than one song, bro. And I'm like, shit. Oh. Like, I fucking love Bollywood, man. I wish more of Hollywood would embrace the craziness and just the unrealisticness of Bollywood and stop being so grounded in reality. Like, the over-the-top ridiculousness is what I fucking love about Bollywood. I have a question. What's up, Rob? Yeah, that's good shit right there. Alright. So here we go. New BookFox video. This is the last one. This one came out 1 day ago, and then we're out of BookFox videos again, guys. We gotta go back to, like, Second Story or something like that. Or maybe we'll move on to, doing narration videos. I don't know.
I once did a poll for BookFox where I asked fiction writers what their main problems were.
Pacing, transitions, and character interaction, specifically dialogue, are my 3 worst things that I'm bad at.
So writers struggle with pacing. They don't know when to go fast and when to go slow and how to manage all that time in their novel. Thankfully today, I am going to solve that problem for you.
Yay!
We're going to go through the 9 steps that every author needs to be able to control the pacing in their novel. Let's start with point number 1, alternate the pacing.
Yeah.
So you don't want
Things need to go fast and slow and fast and slow depending upon what's happening.
Will get tired and they'll burn out. Really, your goal should be to alternate between slower pacing and faster pacing. If you have a scene that's really slow paced and you're like, I'm worried that my reader's going to find it boring, then what you do is you simply place it after a really high paced scene and the readers will welcome the breather. For example, Saving Private Ryan starts with this wild scene of soldiers charging Normandy Beach. It's action packed. It is death filled. There's the clattering.
And then you get straight into the fucking barracks and it's like
is people typing on typewriters. It's slow, it's meditative, and they're typing the letters that say, oh, your son's been killed in action. For another example of this, look at The Hunger Games by Suzanne Collins. You have
what was the question though?
Scene like Katniss fighting in the
you said you have
bloodbath
a question and then you just said bye.
She flees into the forest and the pace.
I mean, bye.
She's looking for water. She tries to find a place to sleep. And if you're not sure how your pacing is, I'd recommend joining BookFox Lab, which is my one-on-one mentorship and coaching program for writers. We're having a great time with the 24 writers currently in our program, and you can join our next cohort. Just check my website for details. The second pacing tip that you absolutely need to know for your novel is dialogue can both speed up and slow down. I used to tell writers you should set a little dialogue alarm in your brain. And here's what I mean by that. If you find that you have a chapter or 2 chapters,
no dialogue throughout the entire fucking story,
all very dialogue heavy, there's a little alarm that should go off in your brain like, I think I've slowed down the pace of my story too much. Clearly, you need to break up those dialogue chapters with a chapter that is more action and events and movement. But I don't mean to apply that dialogue always slows down a book. In fact, I think most of the time, dialogue, if it's just a page or 2, speeds up the story. Let me show you 2 pages from the Italian
This is exactly kind of the last bit of this chapter that we read today in Eye of the World. Like the last 3 pages of the entire chapter are Moiraine telling a story. Oh, I ripped a page. Oops. My bad. That's what I get. But it's 3 entire pages of just continuous dialogue from Moiraine. But it's super fast-paced because what the dialogue consists of is telling you a story from the past and going through like 150 years of events that are happening over those 3 pages. So, because it's a character describing a story, it can add an extremely fast pace to something that would probably take like a couple of chapters, at least in this style of book, to explain.
Those who leave and those who stay. So here we have a dialogue heavy page and we have a non-dialogue page. Let me ask you, which one is faster to read? The one with lots of white space, right? You're gonna blaze through that one because there's not as many words, and that's what dialogue does because you're indenting every single line, so there's less text on the page. So small sections of dialogue, that speeds your novel up. Large sections of dialogue that don't really move the plot forward end up slowing your book down. Now, this next point is the most important thing I'm gonna say in this entire video. It is point number 3, sever scene duration from time. Beginning writers tend to
the greatest tool that you have as a writer is the manipulation of time. It is the one thing that basically every other medium struggles with. Like, in a TV show, you can't just pause the action and have the character go through the character thoughts in their head. But in a book, you can take like 2, 3, 4 pages of like a character meticulously planning something out in their head over the course of like 10 seconds in real life, because they're just like noticing these small things, like in a battle or something like that, like a sword fight, like response being like, okay, if I do this, I need to do that to make sure that I do this to do that so that we do this. So like a sword fight that could take a paragraph, you could turn into 4 pages from doing internal planning and conflict between the character and stuff like that. So being able to manipulate time to your advantage is definitely one of the strongest things you can do in a writing medium.
Write a scene based on how long it takes in clock time. If it would take a long time in real life, then their scene is long. Advanced writers, on the other hand, lengthen or shorten a scene based upon interest. How interesting is this going to be for the reader? If it's going to be super interesting, then lengthen it out. If it's going to be not so interesting, shorten it. And I think the right pacing for your book maintains the appropriate length depending on...
So like a good example is, since we're doing Rebel Weapon today, since I decided like I need, in order to like get for like specifically for them to be written for YouTube videos, the style of writing that I need to use and the way that I tell the story needs to be completely different from how you would normally tell a story. In the fact of, you need to instantly get right into the action and grab someone with the hook. So I'm like plotting out the story, and I'm like, well, what's the most like action heavy moment in the story? And it's like, oh, well, they're going through a hallway and they're attacked by a dog, and this dog is like one of the escaped like earlier infected experiments that they were doing, where they were like using the cordyceps and plants to like modify brain activity in animals to see if they could affect humans as well, to stop the nanobot hive mind from controlling people. And these are just like rogue animals. So I was like, we'll start the scene with the guy being attacked, basically, right? Then we had the stakes of, oh shit, well he got bit by this thing. Is he going to get infected by something, right? And so you just start immediately there, and you go, okay, well now you're on a timer. So you've set the stakes and you're on a timer now, immediately right off the bat of the story. And I'm like, that's the action. That's where we need to be. And then take that, which was originally like the high point of the story, and now we're making that the low point. And now we're going, okay, well, how can we manipulate this experiment? Well, we need the nanobots. Well, then we need more experiments. So let's go to where all the experiments are. So then let's have like a big fight against everyone, have like a couple of people die and shit like that. We're just continuously raising the stakes up, and then it's like, oh, well, we're actually not going to get out of here at the end of the day. But the whole point of being here, like every other story, all of the people always die in the end, but they achieve their goal. And their goal is to like send some sort of information that leads the next group of people in the story for the next story to progress. And it's like that, you know, it maybe one person will escape or something like that, but usually it's like the only thing that escapes is the information. And it's that last stand moment of, can we be here long enough to get the information out? And then everyone dies. And then the next story is like, okay, we got the information, now what do we do with the information? And then it just keeps building up from there until we get to this point of, now in the story we're gonna have the final fucking battle between Lisa's hive mind and the fucking rebellion, and it's like, that's the fast pace right there that we're building up to.
How fascinating it is for the reader. So if it's boring,
but it's like the dogfight scene fast paced, or like, you know, I guess it's like slow paced, even though it's like action, right? It's interesting. You wanna mold that out, and then it's like, well, now we need to figure out what take the experiment. We need to go to the next experiment room. Okay, that all goes super fast, and then boom, we slow down again, and we're in the middle of the battle, and it's like, okay, well, we got to fight our way out of the experiment room. We've got the experiment thing, but now we got to make it to the main complex, and we're just fighting, backing our way around, and then it's like, oh, we're not gonna get out of here, right? And it's like figuring out all the information, all of the data that they need and all that. That's super fast, and then it's like slow down again to them just slowly dying. We're at 98%. They're burning through the door. Bodies are piling up. 99%. Oh, we need that last percent. Hold the line. Some guy throws a fucking grenade, blows himself up. Fucking 100%. Let's go. We made it, guys. That one last puff of a cigar. let's fucking do it. Unload the rest of the ammo, and then the last sentence in the story is the minigun round going like. That you're out of ammo, and that's the end of the story. And you know that they fucking died because they ran out of fucking ammo.
Zip right through it. You know, something like, then we all ate dinner. If nothing happened at dinner, then boom, you've just covered like 1 hour in 1 second of reading time. However, if it's really fascinating, then slow down. Take your time. The reader's going to stay with you because they're engaged in the material. I think of Donna Tartt's The Goldfinch when there's the bombing in the museum at the very beginning of the book. Time slows down, it dilates. She spends many paragraphs, she spends pages talking about the sensory impressions of this young boy who just experienced this bombing. Now, this next point is one you should never forget. It is number 4. Use your sentences to
and that's the length of
this is
the stories, like short, punchy, like we did this versus like the long, drawn out, explanatory.
How fast the reader reads them or how slowly the reader reads them. You can have very long, rushed, frenetic sentences, and that sort of makes the reader read more quickly, or you can have shorter sentences with a lot more punctuation, a lot more periods, a lot more commas, stuff like that, and that will slow the reader down. Now, I want to mention a very special author that I've never mentioned on this entire channel before. His name is Cormac McCarthy. McCarthy has this very famous scene where Native Americans are attacking the mercenaries, and it's just this wild rush of a sentence that just sort of throws you headlong into the action. I'm not going to read all this, but you can pause the video and check it out. It is a wild scene. Sometimes he goes for really long without even including as much as a comma. So of course you're going to read that faster because there's no natural stopping points. On the other hand, check out a book like The Reluctant Fundamentalist by Mozid Hamed. Excuse me, sir, but may I be of assistance? Ah, I see I have alarmed you. Do not be frightened of my beard. I'm a lover of America. The interjections of sir and ah and the commas that accompany that, as well as the frequent periods, it makes us read that a tiny bit slower. I want to give some exceptions though. If you have a sentence which is very long, but it's just a long description or list or something, and there's no movement and no action, sometimes that can actually slow it down. And on the other hand, if you have very...
And I think that's my problem, is knowing, like, I'm only halfway there, because I'm only, length of the sentence and the pauses in the sentence, not the content of the sentence, right? Because that plays a big role in it too, right? Like, what is happening in this sentence?
It can feel like the pacing goes quickly. So these aren't hard and fast rules. It's just something to keep in mind as a way to influence your pacing. I really love this next point. It is number 5. Use information density to control speed. So if
do you want to describe it as blue, or do you want to say that it's from the curvature of the firmament of a clear, fine sky, tipped with sunshine across the center at high noon? That paints a very vividly specific blue color of like a pure sky. But it takes a lot more time to build up that momentum for it.
Have very long descriptions or a lot of world building. That is going to tend...
Or like the, gray splotches on the wall versus like indicating the size and the spacing and the frequency and maybe little tiny oddities of it, right? And you could really go in with that, which is what I love about writing, because my imagination just explodes.
Very heavy, very action heavy. Okay, that's going to speed it up. In Children of Men by P.D. James,
such a good
she
fucking
chooses
movie.
To start the
Never
first
read the
12
book,
pages
but
of
epic
her book
movie.
with sort of this world building of like, look, here's a world in which nobody can get pregnant anymore.
Yeah.
So it's this post-apocalyptic novel, and she doesn't only go into the world building aspect. She also has some philosophizing, like what's wrong with us that we can't figure out
Why we can't have kids
people
anymore.
stopped getting pregnant. That
Yeah.
was a deliberate choice by her to sort of buck the trend of starting with an action scene and just be like, no, like let's talk about this world and what it means for humanity that we're going to die out as a human race because nobody can get pregnant. And of course, after that initial chapter, the book speeds up and we get characters and we get plot and we get action. We get all the ingredients of a faster paced novel. Another great example of how to use information density is Lee Child's novel Gone Tomorrow, and this is a Jack Reacher story. The novel starts with Jack Reacher sitting in a subway car and he's going through this 11-point checklist to determine whether someone else in the car is a suicide bomber. Eventually he gets up and confronts this woman, and the woman isn't wearing a suicide vest, instead she has a gun. And the book does a wonderful job alternating between more action moments. Oh, this woman is pointing a gun at me at a very awkward spot on my body. And then he switches to more information to slow down the scene. So he goes into how much the gun weighs, what the recoil is like. Now, if Lee Child just gave the action in this scene, the whole thing would be over in like half a page. But instead, it lasts 6 chapters. And so what he's doing is he's alternating the action with information, with action, with information, and he has us on the hook the whole time because it's such a tense scene with so much suspense. This is a great example of how to slow down a scene, and also proof that sometimes you do need to slow down a scene a lot more because you have the reader in the palm of your hands.
And
So
you need to
just, like,
capitalize
work
on,
that a
like I
little.
tell everyone,
Make them
this is the moment that I feel that you need to capitalize on this thing that you've set up. And that's like the main reason why I love beta reading and stuff, because I'm stealing all of that in my head and I'm building my own archive of like all of this information of being like, yo, I'm gonna do this in my own writing, right? I'm gonna take these ideas and I'm gonna build on my writing. So it's self-serving in its own way, right?
Sweat a little bit. Let's continue that theme of slowing down with number 6. Slow down with these 2 techniques. I do think that if you're not taking advantage of slower pacing, you miss out on 2 absolutely crucial components of a good novel. The first one is internals, meaning the character's thoughts and feelings. If you're going so fast with your book, you end up just skipping over their thoughts and emotions, which kind of leaves the book a little dry. Now let's look at Normal People by Sally Rooney. It's on my page 65. There is a paragraph that talks all about why she's staying home from school. And it's because her boyfriend embarrassed her by going to prom with someone else, and so she can't bear the shame of showing her face at school. It's about what she thinks of him, it's about what she thinks of herself, and it's not a particularly fast-paced paragraph. It's just her thoughts. But diving into her mind, diving into her emotions, diving into her psychology helps us feel like the book is so much richer of an experience with this actual human being. If you've ever read a New York Times bestseller and walked away from it feeling just a little thin and a little bit unsatisfied, it's probably because they didn't take a couple of moments and just dive into the character's psychology a little bit. The second place where you definitely want to take time to slow down the pacing in your book is so you can have time to cover things like theme. I think of a book like Philip K. Dick's Do Androids Dream of Electric Sheep, which was made into the movie called Blade Runner. And the theme that it's wrestling with is what makes us human? What separates an android robot being from someone who is
Kind of like the theme of
truly
my
human?
book is
it
the
biology?
consciousness
Is it consciousness? Is it
what's
empathy? And if we
what's
can't tell the
fundamental
difference, does
to
the
the different
distinction even
species and
matter? So there are
everything.
parts in this book where it does
So it's like
slow
trying to
down
tell
a
you
little
that
bit to
life
wrestle
is not
with
what
that
it
deeper
seems,
question,
and
that makes the book
despite like the unfairness of the world and stuff, that's the whole point of it, right? The whole point of life is to be unfair, to show you the differences, because you're not just living this one life, you're living all of these lives, and it would be stagnant and boring if every single one of your lives was exactly the same and all great. And it's like, having that mentality of multiple lives, of like consciousness as a whole and never truly losing yourself, always building up on yourself, then you never have this feeling of, oh, my life was wasted. It's like maybe this life was, your last 3 lives were fucking hectic as shit, and now you just want to have a slow, nice, easy life. And then your next one's you're going to get back on the train, right? With that kind of mentality, it gives you so much more to work with the aspect of reality. And how do you interact with reality knowing this? Because you can take it in 2 directions, right? You could say, well, this life isn't worth it because I'm always going to live a different life. Or you could say, just because I live so many lives doesn't make this one invalid. This is me growing as an entity. essentially. And then I have that effect multiplies more to every other entity, so as every individual grows, everyone else around them grows and builds everyone up. And that's kind of my genuine philosophy for how the world and reality is.
That's the core of what the book is talking about. We got 3 more wonderful points in this video. Let's get to number 7. Employ shorter and longer chapters.
Yep. Chapter variation length.
And you can be forgiven for thinking this, that shorter chapters or having a lot of minor little scenes slows down the pacing because there's a pause, right? There's a break. But here's the truth. It takes you almost 0 time to turn the page or for your eyes to skip white space and go to the next scene. So actually it makes you feel like you're reading faster and increases the pace. So here are some books with some shorter chapters, and the length of these chapters
and I felt that through Eye of the World, because it's 800 fucking pages. Like some chapters are 15 pages, some chapters are 5 pages. Chapter we read today was only like 8 pages.
Code by Dan Brown. Dan Brown loves having extremely short chapters. You have The House on Mango Street by Sandra Cisneros, where most chapters are, say, a page or 2 long. Or look at The Curious Incident of the Dog in the Nighttime by Mark Haddon. In this book, you have 51 chapters in 226 pages. So
that's a lot. There's 50 chapters, and this is 843 pages. To put it into perspective,
chapters, it will end up making your book feel a little faster and make the reader feel like, oh man, I'm such a fast reader. I just blazed through this novel. Well, it's because there was extra white space. But don't tell them that. Let them feel like they're amazing.
Exactly.
Another strategy, and this is a really good one, is to alternate between shorter and longer chapters depending upon what the book needs to do, either to speed up or to slow down. Let's look at Jan Martel's Life of Pi. This is a novel with 100 chapters, and a lot of them are super short. Sometimes they're a paragraph long. However, he slows down so much in chapter 9, which is 20 pages long, because it inverts the entire story. This is the climax. It's so important that he gets this right. And he's really upending what the reader thinks about the entire novel, so he has to slow down. This can't be a short chapter. So it's not just a shock in terms of the information he's giving. He also wants to shock you with, we've been going along at this steady pace, this really
and
fast
then he
pace,
just,
and now I'm going to slow down and just like give you a gut punch that makes you question.
That's when you like fall over from momentum, because like the planet stops and your momentum just carries you.
8, the rubber band principle. So the main question that writers have is, how do I know when to slow it down and when to speed it up? This is a great question, and it's very key, because sometimes you're like,
you don't want to pull it to the point that it snaps, but you always want to have tension,
to add 1,000
right?
words. Imagine the pacing on your novel like a rubber band. Okay? You want to have fast pacing, and you can stretch it because that keeps the readers on the hook. But if you keep fast pacing for too long, then the rubber band will end up breaking. So at some points, you want to stretch, and then you want to come back and have discussion of theme, and you want to have some just chit chat and dialogue and have some slower pace, and then you can stretch the pace and speed it up again. So your job when trying to decide whether to speed it up or slow it down is figure out, like, have I been stretching a lot? Have I been really pushing the pace a lot? If so, then take a moment, settle down, like have a calmer scene, and then go for the fast pacing again. And another great thing to do is to get some good beta readers and ask them 2 questions. 1, were you bored at any point? Because that could be a sign that the pacing was too slow and you need to cut down some things from there. And the second thing you can ask them is, were you confused at any point?
Those are the 2 things I focus on. But my problem is, like, I don't get bored easily. So that's why I say it's like more about the idea and less, because the getting bored at any point is more of a the words on the page. Like, whereas the confused is more about the idea, right? Did you make the story exciting? This is, did I understand what you were trying to say? And I focus mainly on what are you trying to say, and did you say it well? Did I understand it properly? And, you know, can I pick anything out of it that maybe you're not, like, aware of that you're doing, right? And so you need to capitalize on this. This is what you, to me as a reader, this is what you set up and then you didn't pay it off. Another goes, well, I didn't intend to do that. And it's like, well, you did. So you either need to remove that or you need to do a payoff for it, because that's ruining it, right? Or you just do this, this, and this, fucking gold, right?
Too quickly. You need to slow
like I said to Relic, like while I read the character introduction, right? And like the backstory, and then I was like, this has like some sort of barrier between me and the character. And then like as I'm explaining this, I'm like tearing up in my head thinking about the character, and I'm like, I should have been feeling this way while I was reading it, but something was preventing me from feeling it. But the fact that as I'm describing it, I'm feeling it means the feeling is there. It's just the writing itself has some sort of barrier that's preventing me from feeling that inner feeling and connecting to the character and saying, fuck, man. Oh man, that sucks. I hope it gets better, but you just know it's going to get worse, and that's what's going to make it so good.
Down a little bit more and allow the reader some time to process the information you've been giving them. Okay, and now it's time for our last point. Number 9. There is no one size fits all.
This is actually something I said today. I was like, you know what? We should probably take this as a motto, and it's like, not all things work for all people. And especially for like giving feedback and stuff like that, I at no point in time do expect anyone to ever take any of my feedback and actually use it, right? Or have any influence on your writing. If it does, you know, that's cool, and I'm glad that I can help, but like it's not an expectation. It is simply I want to make you aware of your own writing. Right? Because I know how hard it is to read my own writing and separate from it and be like, okay, well, is this good? And then when I look at someone else's writing, I'm like, it's not the same as reading my own. And it's even if I'm rereading something that I've known or read before, it's still something that's like, there's just a difference to it because I know that it's mine. And other than that, I just can't explain it other than a bias of saying, well, cognitively, I want it to be good, so I have rose-colored glasses, even though I realize that I have rose-colored glasses, so it becomes this, like, paradox where you have to figure out where's the fine line in the middle that I can get this maximum amount out of. But we're going to have an ad break in a sec here, so we'll wait for the last one for an ad break. We'll just go ahead and take a fat toke here. Fucking ads, their asses. Listen, ads, they're... No. I say no. Don't bring that upon me. I'm innocent, I swear. Please, why would you do such a thing? I could never imagine. All I know is the weed is strong in this one. 3, 2, 1, go! So close to the ads. Please don't mind the gap for the ads, please. As they say, with the passenger with the large melons, please step away from the yellow line. That is the passenger with the large melons. Please step away from the yellow line.
Giving general principles in this video. The pacing for your book really depends on what genre you're trying
what
to
genre
write. If
and
you're
what you're trying to
write
say.
A thriller, then of course the pace is going to be much
If you're writing
faster.
a romance,
If you're
it's
trying
going to be slower.
A character-based literary novel, then yeah, the pace is going to be slower. So there is no right pacing. It's only what's right for your book. Think of the pacing of a Marilyn Robinson novel as opposed to a Michael Crichton novel. One is thoughtful and beautiful and measured and deep, and the other one is action action base and suspense all the time and sort of a lickety-split pace. And remember that different readers want different pacing. Some readers don't want to come to a book and just be hurtled through the plot. They come for a more measured, relaxed, hammocky experience. So yes, you can go too fast in your novel, and it's all about knowing who your audience is and what the right pace is for this particular story. Do not forget to check out BookFox Lab. The link is in the description. It will help you a lot with pacing and everything else with your book. And also, I hope this video has helped your pacing in your novel. Good luck with pacing in your book, and see you later.
The rubber band analogy is pretty good, though. I like that. Yeah. The biggest thing also... What is this jump? What?
I once did a poll for book.
Fuck, now I forgot what I was going to say. But yeah, go check out BookFox. He's fucking awesome. Give him a like, give him a subscribe, give him a view. He is our main... It's been pretty much our main source of... inspiration, creativity, actionable advice, writing notes in general. Very, very helpful. Most, I'd say, of my improvement over the last year has been at his direction, let's say. Because like I said, I have like no formal training or schooling or anything like that in like writing or anything like that. I just enjoy expanding my mind with the creativity of the world. But anyways, we're gonna call it here, guys. So thanks for coming out, thanks for hanging out, thanks for being here. You guys are fucking amazing. And remember, never stop being you. Always be the creative dreamer that you are. Inspire others and allow others to inspire you. And remember, if you can't say fuck you to your friends, who can you say fuck you to? Fuck you. Alright, who we rating today? Who's the lucky one out there? Let's go. Alright, it looks like we got a new one here. Oop. Boop. Alright. Fuck you, we'll see you on the other side. Get your views ready. Here we go. Boop. Alright, and we'll fix fucking OBS so it won't crash on us tomorrow. But yeah, we'll be back again tomorrow. So, fuck you guys.